Today we're going to talk about what you need to know in order to get started programming. It's quite a bit of information, but I think you'll find that it all comes pretty naturally, and also we'll talk about some historical context just to make it a little bit more interesting and engaging. Okay, as a matter of fact, let's start with a question. Why program at all? Here's a quote from a science fiction novel where the author lists all the things that really every human being should be able to do. I don't know if we all agree that we need to know how to die gallantly and so forth, but I think the point is that everyone should know how to program a computer, and that's really the point of view that we take in this course. So that's the first thing. Computers are omnipresent, and it's something that everybody should be able to control. Really what you need to know how to program for is to really get the computer to do what you want it to do. Now, a naive ideal that you might think is, well, why not just tell the computer what you want it to do? Like in this example here, please simulate the motion of n heavenly bodies subject to Newton's laws. It would be nice if we could get a computer to do that. Actually, you're going to write a program to do this in a little while. But it's really naive to expect a computer to really be able to do that. Another alternative is maybe there's a prepackaged solution or an app that does. It's fine to have an app if it does what you want done. And we all have our computers and our mobile devices all littered with apps of all different types. But there's lots of things that there's no app for. What programming enables you to do is to make a computer do really anything you want. Well, almost anything, and we'll talk at the end of the course a little bit about the limitations. And people have realized this for a long, long time. On the right is one of the first computers, Babbage's analytical engine. One of the first programmers was actually a woman named Ada Lovelace. That's a quite interesting story that you might be interested in looking up. So how do we tell a computer what to do? That's programming. The thing is, it's not just for exports. It's a natural, satisfying, and creative experience, just like writing a sonnet or a paragraph. It's actually easier. But the thing about programming is it enables accomplishments that wouldn't be otherwise possible. And we're going to see lots of examples to that. And not only that, it's just a whole new intellectual endeavor that's stimulating just by itself, even if it wasn't actually accomplishing anything. Now, there's some challenges in order to get started, and that's what we're going to be talking about at the beginning of the course. You need to learn what computers can do. You need to learn a programming language, which is a way of communicating with the computer. It's not so easy sometimes to tell a computer what to do, and we often find ourselves in this kind of situation. But I think a more positive way to look at it is a quote from Don Knuth, a leading computer scientist. Instead of imagining that our main task is to instruct a computer what to do, what we should do is concentrate on explaining to a human what we want a computer to do. I think he's talking about really what an ideal programming language would be like. But let's look at it in a little more detail. Now, there are plenty of different ways to tell a computer what to do. When you use an app, you're kind of telling a computer what to do. At the lowest level, which we examine later on in part 2 of the course, there's machine language, which is the computer's language. It's very easy for the computer, but it's pretty detailed and very error-prone for a human to do it. And this is the kind of code that illustrates machine language. This is to add 2 numbers. And we'll have a lecture on that in the second part of the course. There's natural language, as I mentioned. That's easy for the human, but that's pretty error-prone for the computer. And there's plenty of great examples of that. Just getting the computer to understand what you're saying. Kids make nutritious snacks. Red tape holds up new bridge. Police squad helps dog bite victim. Local high school dropouts cut in half. These are actual newspaper headlines, and you can imagine the challenges felt by researchers trying to get the computer to understand natural language like this. So instead, what we use is something in between called a high-level programming language. it's kind of a compromise. It's the same sort of difficulty for both the computer and the human. And the last several decades have shown it's an acceptable trade-off to get us to be able to tell computers what to do. And this is a Java program that's similar to those that we're going to be writing in this course. Now, but which high-level language? Actually, there's a long, long list. There's hundreds and hundreds of high-level languages that have been developed. And one of our big choices in developing this course is choosing an appropriate one. And so, again, there's a naive ideal that there's a single programming language that works for all purposes. That's just not something that can be realized, and for the same kinds of reasons that there's no single natural language for us all to communicate with. We'll talk about that later again in the course. So our choice is the Java programming language, developed by James Gosling a couple of decades ago. The reason we chose Java is that it's widely used, it's widely available, and it's been continuously under development for going on 25, 30 years now. It embraces a full set of modern programming abstractions that now people understand and know are useful. It's got a lot of help, automatic checks to help us make sure that our programs are correct. And there's a huge economy built around Java. It's very, very widely deployed. It's in the Mars rover, it's in cell phones, in disk player, web servers, medical devices, supercomputers. There's millions of developers of Java programs and billions of devices that run Java. So you're not going to go far without finding that your Java knowledge is useful. So that's the reason that we chose Java. Now there's facts of life, and no language is perfect, and there's things about Java that each one of us could think about improving. This is a famous quote by Bjorn Stroustrup, who's the developer of another programming language, C++. He says, there's only two kinds of programming languages, those that people always gripe about and those that nobody uses. So there's going to be problems with Java. We're not saying that, but you do have to start with some specific language, and Java's our choice. Now, our approach is to use a minimal subset of Java that really many of the constructs that we use are found in other languages. And if you do move or use another language in the future, you'll find that a lot of our code is still useful. Really what we're trying to do is develop general programming skills that are applicable to many different languages. It's not about the language. Once you've taken a course like this and learned one general purpose programming language well, you'll find that it's not difficult to move to another one. So long as the course doesn't spend its time obsessing about detailed properties of the language. And we're definitely not going to do that. So let's just take a look at the vocabulary. Sometimes people compare learning a programming language to learning a natural language, but it's actually much easier. That's what this slide is supposed to say. There's only a few different types of things. We're going to talk about all of these things later in today's lecture, and then a few more in the next couple of lectures. But this is pretty much all the words that you're going to use in your Java programs. Almost all the programs you write are going to be made up of symbols like this, plus variable names that we create ourselves. So the language vocabulary itself is quite limited, and you'll find not difficult to learn all these things. And then these things are the tools that you need to write a very broad class of programs. Your programs are going to be these plus some identifiers that you make up, and that's it. So here's your first program. It's called Hello World. Everybody writes Hello World as their first program since at least the 70s. For Java, this program is just going to be typed into a text file. You could type it in an email or use an editor, and we'll talk about that mechanics in just a minute. It's just text. and it's got this specific text in it. The most annoying thing about Java from this perspective is the braces, but they're necessary. That's kind of how you can tell it's a program and not an email message. The thing hello world is the program name. In Java, that program name is the same as the file name that appears right before the .java. And then there's a thing called a main method. And all our programs have main methods, and we'll talk about exactly what that is. And then this program has the body of the main method is a single Java statement that says, in this case, print this line of text out. We go through those elements because every program that you write, or at least the next several, are going to have these same elements. You're going to have a program that you make up, myprogram.java. You'll name it my program or whatever else you want to name it. And it's going to have a main method, and you just type that exact text to get a main method. And then there's going to be a sequence of statements. And we'll talk about what statements are and what they do. But all of this, later in the course, we'll learn about what all these things actually mean. Right now you say, just make sure that you get exactly those characters, and they say to you, this is my program, and that's all. Okay, so let's do just a quick quiz question on this thing, your first program. You've all run, from our first assignments, you've run this program, hello world.java, and it printed out hello world. What happens if you type in your program and you get this error message that says main method not public? Well, or this other one that says invalid method declaration, return type required. Well, in these cases, well, the first one's pretty clear. You must have forgotten the word public, and that's all it's telling you what to do, so you put in the word public. This other one's a little more complicated. We go back to hello world.java to see what it says and match against it. Oh, we forgot to put the word void. Not sure what that means, but need the word void. So you'll get a few error messages like this at the beginning, and then you realize that really you need to type in the exact text that we give in the template. Here's another thing about hello world. Here's 3 different versions of hello world. This is the way that I just showed it on the slide. This is the way that, on the right is the way that Kevin wrote it for our online materials on the book site. And then there's another way that you could write it. And the thing about these different versions is that the color and the actual font, the comments, all the extra space, they're not part of the Java language. We use those to, as a matter of style, depending on the context. They're all the same program as far as Java goes. And I'll talk a little bit more about that in a minute. The thing is that it depends on the context. Different styles are going to be appropriate for programs. The same way is true for a novel or a magazine article or whatever else. We're going to talk about building a program in an integrated development environment. And as I just mentioned, we have programs published on our website called the book site. There's programs in the book. There's programs that I'm showing you on the slides. There's your own code. Those are all different contexts. And so you can, and sometimes people do, insist on a very consistent style on programming. And well, if we really wanted to completely enforce a style and say your program must look like our book site programs, it kind of stifles creativity a little bit. But I think the more important thing is that people get confused about the difference between the style and the language. Doesn't matter how many spaces you indent your statements or whether you put the braces on the same line or not. Those are not part of the language, those are the style. And enforcing a style gets people confused. On the other hand, we do like to usually emphasize consistent style. If you use the same style all the time, it makes it a little easier to spot errors in your programs. The main thing is it makes it easier for other people to read and use the code. So usually in a group of programmers or in a class, people agree on using some kind of consistent style so that they don't get confused by differences in style. But it's not so different than writing essays in a class and so forth. Often a teacher will insist on a certain style to make it easier to grade. Sometimes the development environment insists on a style to give you visual cues to make it easier to write your program. That's another reason. So usually for a student, what we say is what you want to do is to listen to the person that's assigning your grade. Or if you're at work, maybe your boss. There's somebody that wants a style, then you pay attention to that style. Otherwise, my advice is to at least put a little creativity into it and put your own stamp on your programming style. Next, we're going to talk about program development. This is kind of a complicated topic to talk about right at the beginning, but we do it at the beginning because every student writes a Hello World program, but the actual process they use to get that program into existence and running is completely different for lots and lots of students. There's many, many different ways how to actually get the program running. And so what I want to do to answer the inevitable questions that we get about which way to develop a program is more appropriate, I want to put this in a little bit of historical context and also a little bit of understanding of the process of developing any program. So just taking a high-level view, program development in most programming languages is kind of a three-step process with some feedback. So the first thing you do is edit your program. You create it by typing text on your computer's keyboard. And eventually you get a text file like helloworld.java. Then the second thing you do is compile the program. That's translating it from this text format to an executable file suitable for the computer. We use a program called the Java compiler, and that creates a thing called Java bytecode file, which is called helloworld.class, and will be saved on your computer in the same file as helloworld.java. And that's the one that the computer is going to run. Now, sometimes there'll be a mistake in what you typed, like we looked at the example of leaving off the word public and so forth. That's the compiler telling you that's not really a legal Java program, and you have to go back to step one to fix it and then recompile it. You want to keep doing that until you have a legal Java program that the compiler can turn into a bytecode file like helloworld.class. And then the third step is you run your program. And then that's using another part of the Java system called the Java runtime that we evoke from the command line by just typing Java and then the program name. And the result of that is, so that gives the bytecode to the Java machine that, or the virtual machine that's working on your computer, and the end result is your program's output. Now again, maybe your program isn't doing exactly what you thought it was doing, and there might be a mistake. If there's a mistake in the program, then you have to go back to step one to fix it. In this case, you've got a legal Java program, but it's doing the wrong thing. You still have to go back and change the text file, and then recompile it, and then run it again to see if there's no mistakes. So it's a little three-step process with feedback where usually you edit, compile, and run, and if there's ever a mistake, you have to go back and edit again. That's program development. Now this isn't so unusual. Any creative process has this kind of refinement and development. So this is like music. There's compose it and rehearse it and play it, and you have the same type of feedback. Any kind of creative process is going to have this same thing. And maybe there's a few more steps, but it's the same basic idea. But with programming, there's a big difference because we can use the computer to help get this done. The computer can help us find mistakes. And so what we talk about in this process is the idea of a program development environment. That's software that we use for editing, compiling, and running programs. Now there's two there's a lot of different ways to think about program development environments, but I want to talk about two time-tested options. One of them called using virtual programs, and that's an approach that works for many different languages and systems. It's very effective even for beginners, and it's very simple and concise. And there's another approach called integrated development environment, which is often specific to a particular language or family of languages. Sometimes it's useful for beginners, and it gives a variety of useful tools. Most of you use one of these two approaches to get your first program going, and we'll use them for later programs. So I want to talk in a little detail about both in a historical context, and then compare and contrast them. So this is an extremely short history, and again, historical context is really useful in computer science, because one thing is we're always using old software. A great deal of the software that's part of our computational infrastructure was written decades ago. It's surprising and a bit scary, but it's true. Not only software, often new computers emulate old computers so that the old software can run. So we have to know about the old hardware and the old software. And there a lot of the concepts in the designs that were developed 5 or 6 decades ago are really good, and we depend on them all the time. So that's true for program development. So in the beginning, the first computers, people developed programs just using switches and lights on the front panel of the computer. We'll talk about that in the second part of this course. Without much delay, different types of input-output devices like punched cards came into existence, and that's a different way of interacting with computers that people use for quite some time in the 60s and the 70s. Before long, there was the idea of a terminal connected to a computer, and I'll talk a little bit about each one of these on a slide. And it's closer to what I talked about with the virtual terminal. We have an editor, a compiler, runtime, and terminal. It's kind of what we use. And then we use a virtual terminal on a laptop, and I'll talk about that. And then there's integrated development environment. And pretty much since the mid-70s, these two approaches that I'm going to talk about have really been in widespread use. So just a slide on each one of those. Somewhere around 1970, this is an example of a PDP-8 computer. On the heart of the computer is the little panel in the middle there that I've blown up here. And the feature of this was for a significant amount of program development was you interacted with the computer using the switches at the bottom and the lights at the top. That was effective, but a pretty inconvenient way to program, but people definitely programmed that way. And we'll see a lot of detail on that in the second part of the course. The first thing that happens, people said, well, this is too inconvenient, we need better input-output devices. And one thing that worked for a long time was punch cards for input and a line printer for output. So you had a machine that looked kind of like a keyboard, but it would, for every line of your program, it would create a punched card. And so your program would be a physical deck of punched cards. You get a box would hold 2,000 cards, so a good-sized program's 2,000 line program. And you'd actually write with a magic marker on the cards, the different parts of the program. And then there's a huge computer that everybody shared, and over on the right is a card reader. Operator would put the cards in there, and then your program would be in the computer, and then it would print out the result on a line printer. So maybe your parents or even your grandparents, when they learned how to program in college, they used punch cards in the line printer. They can tell you about it. Before very long, what we wound up using, say in the late 70s and 80s, even a little bit into the 90s, was terminals that connected to a big computer. So you didn't have to go to the computer center. You could sit and you had your own keyboard for input and your own display for output. If you wanted to print, you had to maybe fool around a little bit. But the thing was that there were many users could share the same computer. So a small organization could have one computer, and then everybody could have a terminal in their office that they could use to create the text that made up their program, and then to invoke the compiler and the editor, but all kind of sharing the same computer. And that was a welcome development because it got everybody computing in their offices. Now with personal computers nowadays, what we do is use virtual terminals. But virtual terminal just means that we're using the old software that was developed for those terminal devices. So what the keystrokes mean and the output that it gives to the computer in a terminal window in your computer is precisely the same as those physical VT100 terminals. That was one that was widely used. So this is just what my screen usually looks like when I'm programming. There's a virtual terminal for the editor. And then I have a different virtual terminal that I use to compile, run, and examine the output. I usually also have a virtual TV set, maybe with a Red Sox game on it. No virtual TV set, virtual terminal, you get the idea. So I can type javac hello world.java in a virtual terminal, and then I can type java hello world to run it, and then I can see the output. So really this whole setup, which is on my personal computer, is using old software in a convenient way, but it's a fine way to edit, compile, and run programs. And many, many professional programmers work in this way. You can have multiple programs displayed on a big screen, and you can have multiple virtual terminals going to run them in different contexts and so forth. But this basic idea has held up at least since the 1980s, and plenty of people still use it. Another idea is this idea of a customized application for developing a program in a particular language, so-called integrated development environment. This is one called Dr. Java. And there's other integrated development environments that are appropriate for Java programs. One of the downsides of integrated development environments that I'll talk about is that they come and go like languages come and go. Whereas virtual terminal, you can use the same environment for many, many different languages. So anyway, it's got a button in there. It's an application for developing Java programs. So it's got a button for compile and a button for run. And then it's got a command line where you can also see the output. So then it's just a different approach to developing programs. So what are the pros and cons of these two different approaches? Well, as I mentioned, virtual terminals works with any language. You can be doing things, controlling the computer without programming in Java. You can be programming in some other language or invoking other commands or deleting and moving around files and many, many other things in your virtual terminal. So lots of, as I mentioned, lots of professionals use virtual terminals for program development and other ways to control the computer. It really has withstood the test of time. If you've got something that's been in continuous use since 1970, it's probably good for something. Now the thing about an integrated development environment, some people feel it's, you've got language-specific tools that make it a little easier, a little more convenient to develop your program. You have line numbers, you have color highlighting and other things like that. People do create system-independent integrated development environments, so a new computer comes along and uses the same environment, at least in theory, although as I mentioned, they come and go. And these types of systems are used by professionals to create, particularly to create huge programs. And also, they've got a lot of error checking and hints and other things like that that can be helpful for beginners. So the problem with virtual terminals is that if you have a huge program, a really long program, lots of different modules, you might need the help of something that understands something about the programming language that you're writing in. And so the IDE would be better. And you're dealing with a bunch of independent applications, the terminal, the editor, the Java runtime, and so forth. So anytime any one of those changes, you have to deal with it. And maybe people feel maybe you're working at too low a level when you do the virtual terminal. So for integrated development environment, for Hello World, that's really a lot of machinery to fire up for short programs. And when you're learning first couple of years, you're basically writing short programs. So it might be kind of overkill. It's a huge application that has to be learned and maintained. If there's a new version of your operating system, the application, you know, then these are complicated applications. So you might be problems as time wears on with integrated development environment. And a lot of times it's specific to the language. A new version of the language comes out, the IDE might not catch up, or you move to a new version of your system, your old IDE might not work. And those types of problems are definitely there. So because they're so simple and concise and precise, we talk about terminals mostly in the lectures and in the book, because there's too much information if we were to show a program in an IDE. For assignments, a lot of people are going to recommend that you use IDEs, although you'll find plenty of programmers and bosses that'll say, oh, just use virtual terminals, you'll be fine. So those are the trade-offs. We have many students that use both either system, and that's the story on program development. So what are the lessons? That every computer's got a program development environment, and actually multiple, that let us go through this cycle of editing, compiling, and running. Using virtual terminals, using an integrated development environments have worked for, both of them have worked for decades, all the way from the first personal computers like the Xerox Alto or the Apple Macintosh, all the way up to today's computers. Now we're going to get into writing some actual Java programs. And to get started, what we need to do is talk about the types of data that you can use and manipulate in Java programs. And we're going to start from the beginning with the data types that are built into the Java language. So what is a data type? Well, it's a very well-defined concept. A data type is a set of values and a set of operations on those values. And right now in this table, we'll look briefly at the built-in data types for the Java language. So there's a type called char, and that's the set of values is the characters that say we type on the keyboard. So like A or @ sign or 1, 2, 3, 4, any character that you can type is of type char. Now, those are the values, the operations that you can do on those values. Well, you can compare characters, and we do that to put words in order and other things like that. We'll see. One thing that we do with characters is we put them together to make a type of data called string. A string is a sequence of characters. So examples of a string, in Java we put them in double quotes, is hello world or CS is fun. Any string of any sequence of characters within double quotes is a string. The operation that we perform on strings is called concatenation, and we'll look at that operation in detail. And then there's numeric data types. At the beginning, we write programs that manipulate numbers. It's the same way in history. Computers were developed in order to write programs to manipulate numbers for scientific, commercial, engineering applications. One type of number is an int, so that's just an integer. And so like 17 is an integer, 1, 2, 3, 4, 5 are integers. And the operations that we perform on them are the standard arithmetic operations like add, subtract, multiply, and divide. We also work with real numbers. In Java, the data type double represents floating point numbers that you're familiar with from science. And so that's like 3.145 or 6.022 times 10 to the 23. Floating point numbers are approximations to real number, or are real numbers that usually approximate the numbers that we want. And again, we can perform the operations of add, subtract, multiply, and divide. And then there's a data type called boolean. The set of values for boolean is just truth values, true or false. And the operations that we can perform are and, or, and not. We'll talk about each one of these in more detail next, along with programs that use basic operations to manipulate variables that are of these types of data. So everyone has to know the answer to this question on any exam that I write. What is a data type? It's a set of values and a set of operations on those values. If you really internalize and understand this definition, you go a lot further in programming than if you don't. Now, in terms of manipulating data, we have some basic definitions that appear in all our programs. So the first thing is a thing called a variable. That's a name that refers to a value. So in this case, A and B are variables. This is a short program that adds two numbers. Then there's a thing called a literal. That's a programming language representation of a value. So for an integer, literal is a string of digits, 1 to 9 and 0 to 9. Then there's a thing called a declaration statement. That associates a variable with a type. So these two declaration statements say that A and B are of type int. So the set of values that they can take on is the integers, and the set of operations you can perform on are add, subtract, multiply, and divide. Then the other kind of statement that we're going to use for most of the programs today is called an assignment statement. And what that does is associate a value with a variable. So this one associates the value 1, 2, 3, 4 with A, and the second one associates the value 99 with B. Then this last one, you can actually combine a declaration and an assignment statement. So let's look at a really simple example of a complete program that uses all of these concepts. So what happens is that we have two variables A and B, 1, 2, 3, 4, and 99 that we set up like on the previous slide, and they're both int values. And then this is a program that exchanges the values of A and B. Usually, at the beginning, to understand what our programs are doing, we write a table called a trace that just gives the variable values after each statement. So we start out with none of the variables declared. We say int A equals 1, 2, 3, 4, then 1, 2, 3, 4 is associated with A. That's what the table shows. B equals 99, 99 is associated with B. That's what the table says. And then T equals A takes the value that's 1, 2, 3, 4 and associates that with T. So after that statement, T is 1, 2, 3, 4. Now the assignment statement is not equals like mathematical equality. It really says associate the value with the variable, which is different. Okay, so now we say A equals B. So we find the value associated with B, that's 99. We can see that from the trace, and then we associate that with A. And then B equals T, then we have the 1, 2, 3, 4 associated with T, and then we give that value to B. So that trace of these 5 statements tells us what that program does. The question is, what does this program do? And actually, if you type in this program and run it, well, nothing's going to happen. There's really no way to tell what it did. We need some output for that. So we have to put a print line like for hello world, and we'll talk about that in just a second. But what the program does is exchange the values. Okay, so in order to provide that output so that we see it when we run the program, that's what we use strings for. Again, the string data type, the values are sequences of characters in between quotes. Our operation is concatenate, and we use the plus sign to indicate that we want to concatenate strings. And so if we write an expression using the operation, If we take two strings and put a plus sign between them, then it just puts the second one after the first and makes a new string that contains all the characters in the first string followed by all the characters in the second string. It doesn't matter any string at all. So this is the string 1 concatenated with the string space 2 space, concatenated with the string 1, and then you get 1 space 2 space 1, and like that. Concatenation operation. So you have to pay a little attention because the meaning of each character depends on the context. If a plus is within quotes, it means the character plus. If it's not within quotes, it means the concatenation operation. So in this first case, we get the plus character. In the second case, we just get a bigger, a longer string of digits. So again, the interpretation depends on the context, and I just gave that one example where two of the pluses are operators and the other one's a character, and this is another one with spaces. If the spaces are outside the quotes, Java doesn't care about them. You can put any number you want. If they're inside the quotes, they're part of the string and they're significant. So that's computing with strings. And why do we compute with strings? Well, we want to put together output that we print on our terminal window so that we can see what our program did. That's why we talk about strings right away. We use them for input and output. So, but you can also write programs that compete with strings. Here's a program. And the goal of this program is to print the heights of the divisions of a ruler. So the little line under the 2 is, say, 4 units high. The ones at the half inches are 3 units high. The ones at the quarter inches are 2 units high. The ones at the eighth inches are 1 unit high. And if you write out this string 1, 2, 1, 3, 1, 2, 1, 4, 1, 2, 1, 3, 1, 2, 1, we want to write a program that does that. And this is a really simple program that accomplishes that goal just by building up, using concatenation to build up a big string. Now, all the operations are concatenations. And again, we can write a trace to see what this thing does. So the first thing sets ruler 1 to just the 1 string. And then ruler 2 is that 1 plus space 2 space plus another 1. And then the next one takes that string and then puts a 3 and then another copy of that string. And then ruler 4 does it to get 4. So a simple 4-line program. And then if we want to see what string we got, all we have to use is print line, just like we did for hello world. With hello world, we had the string hello world. Now we've got the string ruler 4. And so when we run this program, we get this string printed out. And we've got a program that computed something interesting just with string operations. So we type Java ruler, we get that string out. Computing with strings. Okay, so we need input and output, and we use it for the result of our computations. The thing is, especially at the beginning, very often our programs are working with numbers and we're working with strings. So for output, we use system.out.println to print the string. And even if you print numbers, Java will automatically convert the numbers to strings to output them. For input, if you type Java in a program name, any strings you type after the program name are available to the program. And we'll look at how to get information into our program as strings from the command line. So those are the two ways at the beginning that we're going to use input and output to get information to our program and to learn what it did. Those things that we type are strings because we're typing them. How does Java know if we type 1, 2, 3, 4 whether we mean the string 1, 2, 3, 4 or the integer 1234? Well, there's a system method that converts that, and we'll look at the use of that in just a second. Before very long, we're going to look at lots of different options for input and output, and also lots of different options for converting types. But we need to talk about these few just to get started on the rest of the programs that we're going to look at today. So, as I said, when we had this exchange values program, we don't know what it did unless we print out the results. So if we add these two print line statements to this program, again, A and B are integers. They're data of type int, they're integers, but Java will automatically convert them to string for output. So if we type Java exchange, and the other thing is that this program takes from the command line two arguments, args0 and args1. They come in as strings. We call parse int to get them converted to numbers, and that's what we set to A and B. So they start as strings, they become numbers, then the code exchanges them, and then when we print them, the result gets converted back from numbers to strings. And so what does this program do? It reads two integers from the command line and then prints them in the opposite order. It actually reads strings, converts them to integers, exchanges them, prints them out in the opposite order. So just looking at this program now, it's a template for lots of programs that we can write where we provide parameters as strings that are easy to convert to numbers, process the numbers, and then print them out with the system automatically converting them back to a string. So now we can look at computing with integers. So the int data type, again, what's the set of values? In a computer, it's got to be finite, and we can talk about the details, but in Java, the set of values for an int are the integers between -2 to the 31st and 2 to the 31st minus 1. And this range has to do with the way the integers are represented within the computer. And it's useful for typical applications. And again, literals are just strings of digits that represent integers in this range. Now operations, add, subtract, multiply, divide, and remainder. And again, there's only 2 to the 32 different int values. So they're not quite the same as real integers, which could be bigger than that. But for many purposes, they're useful enough. And then we can do operations like add two integers, subtract them, multiply them. If we divide two integers, then the result we get, they drop the fractional part so that the result is an integer. If you take the remainder, you get the remainder of the division or the mod operation. And if you divide by 0, that's an error. You'll get a runtime error from the Java system. We can write longer expressions, and there's a concept called precedence. If you write an expression that's got a couple of operations, which one's going to get performed first? Well, multiplication and division are going to happen before addition and subtraction. So in the first case, the multiplication gets done, so that's 15. Then you subtract the 2, that's 13. In the second case, the division happens first, and it's 2, drop the fractional part, and then add the 3 to get 5. If you write a couple of operators that have the same precedence, Java's expressions are so-called left associative, which means the one on the left gets done first. But it's better style to use parentheses to express your intent as a programmer and not try to trick the person reading the code. So we're going to see lots of examples of programs that manipulate integers, and we're going to use them for math calculations and other applications. So this is an example of computing with integers. And again, just to make sure that everybody's thinking carefully about the difference between integers and strings and type conversion. So take a look at this program for a minute and try to see what it does. Again, one thing that I didn't mention is that if you take a string and you add it to an integer using the plus operation, Java figures out that really what you meant to do was convert that integer to a string and then go ahead and concatenate. So it's another automatic conversion that Java does, convert the int values to string for concatenation. Then with that piece of knowledge, you can see what this program does is it takes 2 arguments from the command line. Then it performs the basic plus times divide mod int operations, the sum, the product, the quotient, and the remainder. Those are then computed, and they're a part of Java's int data type, so they're integers, those values. And then it prints out a string that represents the expression that it computed. It takes the int a, and so in this case it's going to be 5, and then it concatenates that with plus, space, and then puts the b, and then space equals space, and then puts the sum, and it does that for each of the 4 operations. So you get a little table defining the result of Java's computation for these operations. And this is a nice program to make sure that you understand what's going on in terms of type conversion and integer and string operations. That's just computing the remainder for you. Okay, next we're going to look at a data type for computing with floating point numbers, the double data type. So again, the values for double data type are floating point numbers or scientific notation. So this one is 6.022 times 10 to the 23rd, or 3.14159, and like that. And again, the operations are the familiar arithmetic operations. Now, it's important to remember that often, or typically, double values are approximations to the actual number you might be thinking about. Like, there's no double value for pi. A representation within the computer can only have a finite number of values, or for square root of 2, or even for 1/3. In Java's representation, there's no double value. There's one that's extremely close, but it's not exactly equal to 1/3. And that's something that we have to take into account when we're writing programs that are working with approximations to real numbers. So these are the types of expressions that we write with double. And again, we get the results pretty much that we expect for math computations. Get good approximations to the numbers that we want. In the case of double, there's some special values. So if you say 1 divided by 0 with doubles, there's a special value called infinity. And you can compute with infinity and get the kinds of results that you expect. But there's also not a number. If you take the square root of -1, that's not a real number, and there's a value, not a number, that you can work with as well. Those are the basic values and operations for the double data type. And again, we use this for scientific calculations, and we'll see plenty of examples of programs that do scientific calculations with this type of data. There are other built-in types for representing numbers in Java that we don't use too much, but sometimes. There's one called short, which is same operations as int, but smaller set of values. And another one called long, which is same operations, but a much larger set of values. And there's one called float that is like double, but it's a smaller set of, it's less precise. And so the reason that we have different numeric types is that it's a trade-off between how many bits do we want to use to represent the number. And for integers, it's a straight trade-off, is what's the range. And for real numbers, it's how much precision do you want to get with the number. And I guess the range as well. Without going into a lot of detail, but short is 16 bits, int and float are 32, and long and double are 64. And it's important to be aware of these kinds of restrictions and really knowing what the set of values is, because you can get into situations where it's important. And we'll talk about a situation like that in a bit. Now with doubles, we have lots of built-in functions that we can use to compute on double values. And actually, a lot of them work for int and other types as well. So you can get the absolute value, you can get the larger of 2 values or the smaller of 2 values. You can compute the sine function or the cosine or the tangent or the arcsine and so forth. And it's done in radians, but there's functions to convert back and forth to degrees. There's the exponential function, there's the log function, which is a natural log. There's a to the bth power. There's round to the nearest integer. There's random, which gives a random number that's between 0 and 1, but less than 1. There's square root. We're going to actually talk about how we might implement the square root function later on. And you can get the value of e and pi. So with these kinds of functions, we can write programs that do lots of familiar computations from science and math. And one thing that you can do is, if you have a calculator, throw it away because you don't need it, because you can write Java programs to do anything that your calculator does. And the advantage is the Java program can be long and complex, but it's a text file, and also you can save it and use it again quite easily, the same way that you save all kinds of other information on your computer. So with the math library, we're already past the calculator. So here's just an example. So if you want to have a polynomial x squared plus bx plus c, then you can find the roots using the quadratic equation. So what are we going to do? Well, we're going to take the coefficients from the command line, that's the b and c, and these are of type double, so they're going to be strings, but we don't want them to be integers, we want them to be of type double because we're going to do things like take the square root. So we use double.parse double, whereas before we used integer.parse int. So we take the two things from the command line and put them in b and c, and then we do the quadratic formula. So first we compute b squared minus 4c. So that's going to be a value of type double that we call discriminant, and we write the expression b squared minus 4c. A lot of times when we're computing with doubles and we have constants, integer constants even, we write 4.0 rather than just 4, just to make sure that it's a double literal. Then we take the square root, that's d, and then there's two roots, minus b plus the discriminant over 2 and minus b minus the discriminant over 2, and then we write them out. And these things are double, but again, if you're writing it out, Java automatically converts it to a string. Roots of x squared minus 3x plus 2 are 2 and 1. That factors into x minus 2, x minus 1. As you remember from grade school. This is x squared minus x minus 1, and one of the roots of that is the golden ratio. X squared plus x plus 1, roots are complex, so we get not a number. And if we type something that's not a double, I want to know the roots of x squared plus x minus hello. That's not a number, and I get a runtime error saying it's not a number. And if I leave off an argument, well, it's not always the case that the error message is crystal clear telling you what it means. In this case, what it means is I wanted 2 arguments, you just gave me 1. You're certain to get this error message. People get it all the time, not really remembering how many arguments they're supposed to type. And we'll later on learn exactly what it means, but a lot of times you're going to get error messages you don't know what they mean. You're going to have to study your program to figure it out. I'll be talking about that in a lot more detail later on. So that's a program that computes with floating point numbers. And again, any math equation now, you've got the tools to do the calculation, any kind of calculation that you might want. Maybe a little less familiar is the Boolean data type. It's kind of simple, but it's also kind of fundamental. And we'll use it kind of immediately, but it plays a more profound role in computing later on. For Boolean, the values are true and false. The literals are true and false. There's only 2. And the operations are the logical operations and, or, and not. The operators that we use for these operations are double ampersand for and, double bar for or, and exclamation point for not. And they are completely defined by these tables. So if A is true, not A is false. If A is false, not A is true. And for the other operations, this table gives all 4 possibilities for A and B. A and B is true when they're both true, false otherwise. A or B is true if either one of them is true, and false only when they're both false. There's other Boolean operations. For example, there's an operation called XOR. And that one, actually any Boolean operation can be expressed in terms of and or not. I won't quite take the time to go through this, but for any Boolean function, in this case exclusive OR is false if they're both the same and true if they're different. And this little table is a proof that that operation is expressed by that Boolean expression. And we'll get back to this and see other examples later on. Right now we just want to use really simple examples with and not and so forth. And we're going to use these to control the logic of a program or the flow from one statement to another. Boolean operations play an important role in that, and we'll see that very soon. So for each type of data, there's fundamental operations built into Java that allow us to compare their values, and that's very important in lots of computations. So these operations, the operands are two expressions of the same type, and the result is a Boolean. So usually, so it's either true or false. So just for example, there's the equal comparison operator. So you've got two ints and two equal 2, that's true. 2 equal 3 is false. And then there's not equal, which is the opposite. And it's less than or equal, greater than or equal. So we can take values from a data type, two values of the same type, and then we can perform these kinds of operations on them. All our types, the way they're compared is natural. The numbers is natural order of the numbers. The string is the lexicographic or alphabetic order. This is an example of when you might want to use these types of operations in a program. Like maybe you want to test in the program that for the quadratic equation that the discriminant was positive. So you might want to know, is b squared minus 4ac positive or non-negative or not? So you just say, is it greater than or equal to 0? Now you have to be a little careful because double values are approximations, but something like that's probably going to be all right. So you want to know, you've got a variable year that gives a year, and you want to know if that's the beginning of a century. So you test whether when you divide it by 100, you get a remainder of 0 or not. And that's, again, these things have a value of true or false, and then in a minute we're going to see how we might compute with those true and false values. Or you have a variable month that's between 1 and 12, and then you can say, okay, is it greater than or equal to 1 and less than or equal to 12, just to check that it's legal. So there's lots of times when we want to check the values of things and get a true or false result. That's what comparison operators do for us. So here's an example of computing with Booleans. Is a given year a leap year? Well, so the rule is that it's it's definitely a leap year if it's divisible by 400, or if it's divisible by 4 but not 100. So that's the rule. So here's how to write a program to implement that rule. Again, we've got leapyear.java. It's got its name leap year. It's got a main, and now we write our program. So we're going to take the year from the command line. It's going to be an integer value. We're going to compute a Boolean value that says true if it's a leap year, false otherwise. So is it divisible by 4 but not 100? Well, we'll say year divided by 4, the remainder when you divide by 4, is that equal to 0? It's either true or false. So we want it to be divisible by 4, so if it's divisible by 4, that'll be true. And year, remainder when year is divided by 100, not equal to 0. So this whole expression now sets leap year to true if it's divisible by 4 but not by 100, and false otherwise. And then, well, if it's divisible by 400, then we also want to make it true. So we say it's either that thing, or if the remainder when we divide by 400 is equal to 0. So then we print out that value, and that's going to be either true or false. So now we have a program that we can keep on our computer, and any time we can type and say, okay, is 2016 a leap year? And it says yes. 1993, no. 1900, No, but 2000, yes. Example of computing with Boolean data types. We're going to finish with a brief discussion of converting from one type to another. We've already touched on that several times, but it's worthwhile to take a look at it explicitly. Now, the thing about the computer language and the concept of data types is the variables involved in a data type operation have to be of the right type. It's only defined for that. And that's why we appreciate the idea that the Java compiler can check for type errors in the code. If we try to add an integer to a string, it'll tell us, well, if we try to add a boolean to a double, it'll tell us that you can't do that kind of operation. So there's a string times 2, and it's going to say, you can't multiply an integer times a string. That's an error. And that's a good thing that the Java compiler will tell us about that error, because sometimes there might be conversions that happen automatically that we might not expect. But a lot of times, as we've already seen, we want to convert from one type to another to make types match in an operation where it makes sense. So with the built-in types, it's really converting is an essential aspect of programming. We have to worry about it. There's 3 ways that it can happen. So we've already talked about automatic. If we have plus and one of the arguments is a string, it's automatically going to convert. And the other is a number, it's automatically going to convert that number to a string to get the concatenation done. If you're trying to use a float and an integer in the same expression, it'll go ahead and make the conversion if there's not going to be any loss of precision. So 11 times 0.25, it'll convert the 11 to a float, and that'll be the right type, and it can perform the operation. Sometimes we need to explicitly define a type conversion, like with a function call. Integer.parseInt returns an int, and it's going to explicitly make the conversion of the string into an int value. Math.round is another example. And then there's a third type of type conversion is called a cast. So that's what we use for values that belong to multiple types. Like small integers, like 2 or 12, can be either short, int, or long. And also double values, we can truncate them to int values. Sometimes that's what we want to do in the computation. And the way that we make these types of type conversion is just put the type that we want in parentheses before the number. So if we say int of 2.71828, it'll truncate to give an int value that can be used in another expression. So those are examples. 11 times int of 0.25. That int's going to be truncated to a 0, so the result will be 0. And we look at these types of expressions, and there's many examples in the book and in the exercises, and it's important to always know the type of your data, because if you're not aware of the type of data, it can lead to problems. Sometimes type conversion gives sort of counterintuitive results, but it's much easier to understand with some practice, and that's why we highlight it right at the beginning. So here's just a couple of questions that, again, you might find on a quiz. So 7/2 times 2.0. So what's the type of that, and what's the value? 7 over 2 is inside parentheses. So that's going to be integer division. So it's going to throw away the remainder. It's just going to be 3. And then multiplying by 2.0, that 3 will get converted to a double. So then the operation star is 2 doubles, and the answer will be 6.0. If you do 7/2.0, then you get inside the parentheses 3.5, because the 7 will get converted to a double, because the other operation's a double, so that's 3.5. And then that 2 on the right will get converted to a double, so we have a multiply with 2 doubles and you get 7.0. It also gets a little confusing with strings. So the string 2 plus 2, well, Java automatically converts the right-hand argument, which is a 2, to a string, and so you get 22 and the result's a string. 2.0 plus 2, well, again, that's a string. If either argument's a string, it's going to convert the other one to a string. And so anyway, those are some examples of type conversion. And it's a good idea to work through some examples like this. So this is just an instructive modern-day story about type conversion. Again, why do we have different numeric types? It's because if we want to have a big range, we're going to have to use memory for integers. And if we want more precision, we're going to have to use more bits for floating point, and that's why we have these different types. Now, but the thing is that because of the restrictions on the range, it might be impossible to do a conversion sometimes. So for example, say I have the number 70,000 and I say, okay, I want to cast that to a short, so I could write short 70,000. Well, that's not possible because short values have to be between minus 32,768 and 32,767. There's only 16 bits. Can't do that conversion. Well, what do you do if there's an impossible conversion? Or what does the system do if there's an impossible conversion? Well, there's a couple of approaches you could use. So the one that we advocate the most is make sure that you avoid doing it in the first place. If you write that cast, make sure that you know that the thing's in the right range. Java's approach is say, okay, there's going to be a well-defined result, and you're going to have to live with it. And you can check and so forth, but anyway, that's Java's approach. And another approach is to not check for it, not live with it, just crash. And by crash, we mean actually crash. A type conversion error of this type actually led to the Ariane 5 rocket blowing up in 1996. They switched to a different representation, and there was a cast that was impossible, and one of the control variables had a bad value that caused the rocket to crash. You have to pay attention to the type of your data. Here's an example of type conversion put to good use, and this is our last program of the day. So we've got math.random that gives us a pseudorandom double value. What if we want to get a pseudorandom integer value between 0 and n minus 1 for any given n? Like if we want to roll a die, we make n equals 6. Or if we want to draw a card, we make n equals 52. So what we're going to do is take the value n from the command line. Again, string to int system method. Then we're going to get our random double value, a number between 0 and 1, but less than 1. And then what we do is multiply r times n. That's going to give a result that's between 0 and n, but less than n. And then we're going to say, okay, now you can truncate that. And that'll give you, first the n get converted to double to do the r times n. And then there's the cast to truncate once that's done, and the result is an integer value between 0 and n minus 1 that we just print out. So now we can roll a die, and we get different random values, or if we want a random value less than 10,000, we can get that too. So that's knowing the types of your variables and using them for a useful computation. And we'll use this one actually a lot in this course. So that's the summary. A data type is a set of values and a set of operations on those values. There's a lot of commonly used built-in data types for Java that we've seen programs that use them. There's string for input and output, which is strings of characters. There's integers and doubles that we use for science and math calculations in programs. And there's boolean that's computing with true-false values that we're going to use for decision-making in programs. So in Java, you must declare the types of your variables. That's not true in all programming languages. You must convert from one type to another when necessary. And you must identify and resolve type errors in order to compile your code. Java compiler will not let you go on if you're doing something like multiplying a string by an integer. You have to pay attention to the type of your data. I emphasize this because it's an important distinction between Java and some other popular programming languages. The compiler is your friend. It's going to help you identify and fix the type errors in your code, and you're going to have much better and more reliable code as a result. Next time we'll talk about writing programs that have more complicated control structures and perform lots more interesting tasks.